that a relation R is defined on a set A as the subset of A cross A. That is, R is a subset of A cross A. Okay. Obviously, we know that subset of A cross A, phi and A cross A, ठीक है, are trivially two subsets of A cross A. So we can define R equal to phi as a relation, and also R equal to A cross A as a relation. R equal to phi is called an empty relation, or null relation, or void relation. Whereas R equal to A cross A is called universal relation. An empty relation means no element of A is related to any element of A. इसका मतलब है कि R इक्वल टू फाई एम्प्टी रिलेशन, यानी कि किसी भी एलिमेंट सेट A के किसी भी एलिमेंट का सेट A के किसी दूसरे एलिमेंट से कोई संबंध नहीं है, R इक्वल टू फाई. Whereas R equal to A cross A, it means all the elements of A are related to each other. Clear? Now, reflexive relation. For every A belongs to A, A comma A belongs to R. A relation R is said to be reflexive relation if A comma A belongs to R for every A belongs to A. It means we can also write it as A R A for every A belongs to A. Read as A is R related to A. A is R related to A for every A belongs to. Here the important part is this: for every A belongs to A. For every means every element of A. What it has? A comma A, ordered pair A comma A, means image of element A is itself A. इसको सिंपल भाषा में कहें कि प्रत्येक एलिमेंट्स की मिरर इमेज होनी चाहिए. यदि रिलेशन रिफ्लेक्सिव है तो एवरी एलिमेंट हैज ए मिरर इमेज. फॉर एग्जांपल, लेट A equal to 1, 2, 3. Now we can define R equal to 1, 1, 2, 2, 3, 3, 1, 2. Now we can see that here elements of A are 1, 2 and 3. So by the definition of reflexive relation, we must have image of 1, 1, image of 2, 2, and image of 3, 3. So the only necessary ordered pairs for the relation to be reflexive, yeah, 1 1 2 2 and 3 3. There also can be any other elements, any other ordered pairs, 1 comma 2 or etc. So the only requirements here is that all elements must have mirror image, that is 1 1 2 2 3 3. Whereas if we have, for example, 1 1 2 2 1 3, obviously we can see here the element 3 does not have an image, means ordered pair 3 comma 3 does not exist in R2. So this relation is not reflexive. So whenever we say a relation R is not reflexive, it means at least one element of A does not have an mirror image. कम से कम एक एलिमेंट ऐसा होगा A का जिसकी मिरर इमेज नहीं होगी, तभी वो रिलेशन रिफ्लेक्सिव नहीं कहलाएगी। अदरवाइज सारे एलिमेंट्स की इमेज आपको मिल रही है सेम, तो वो कहलाएगी रिफ्लेक्सिव रिलेशन। व्हेन वी से ए रिलेशन R is not reflexive, R is not reflexive if there exists an element A belongs to A such that A comma A does not belongs to R. So in this case relation is going to be, in this case relation is not reflexive. If difference in this language and this language, here the word is used for every, and here is no such word, only A belongs to A, यानी कि any element belongs to A. Clear? So important point in reflexive relation is for every. For every, it means every element of A must have a mirror image. Clear? If any element of A does not have a mirror image, then it is not reflexive. Clear? This relation R1, it is reflexive, and this is R2 is not reflexive. Now we come to second type, symmetric relation. A relation R is said to be symmetric if A comma B belongs to R implies B comma A belongs to R for every A comma B belongs to A. यानी कि A relation R on a set A is said to be a symmetric relation if A comma B belongs to R implies B comma A belongs to R, where A and B are the elements of set A. Here the important thing is this element A comma B. If any relation contain an ordered pair A comma B, if it is symmetric, then it must contain B comma A. In other words, it can also be written as A R P implies B R A for every A comma B belongs to A. Now we come to the important point, not symmetric. A relation R is said to be not symmetric relation if A comma B belongs to R, but B comma A does not belongs to R. Here the important thing is a pair must exist in relation R, A comma B, but B comma A must not exist in R. If situation is like this, then the relation is not symmetric. Example, let A equal to 1, 2, 3 and R3 equal to, let us consider 1, 2, 2, 1. You can see here, if the element 1, 2, a pair, ordered pair 1, 2 belongs to R, then the reverse AB, BA, a 1, 2, 2, 1 also belongs to R. This one or this one. So the relation in this case is symmetric. Whereas if we write only 1 comma 2. Now here this pair A comma B, any element 1 comma 2, ordered pair 1 comma 2 belongs to R, but this R4 does not have 2 comma 1, so this relation is not symmetric. Now think about the relation phi, means empty relation or null or void. It does not contain any ordered pair, or it does not contain any element in relation R5. So here this element, if you search A comma B belongs to R, you will not find this element in R. So this relation is trivially symmetric. Trivially symmetric. Trivially का मतलब by default. We cannot say it is not symmetric, since the violation of this rule does not exist in this. It is necessary to have an ordered pair A comma B belongs to R and B comma A does not belongs to R. If this condition is not satisfied, then we cannot say it is symmetric. Clear? So R phi equal to phi is also a subset of A cross A. Obviously it is a relation and this relation is symmetric. We cannot say it is not symmetric. Okay, now we come transitive relation. A relation R on a set A is said to be transitive if A comma B belongs to R, B comma A belongs to R, B comma C belongs to R implies A comma C belongs to R for every A, B, C belongs to A. More precisely, if there exist two ordered pair such that AB and BC, second element of first ordered pair and first element of second ordered pair are same, you can see. AB, BC. If there exists A to C, A comma C belongs to R, or in other language, A R B, B R C implies A R C. For every A, B, C belongs to A. In this case, relation is said to be transitive relation. In simple language, you can understand. Let us consider A is a friend of B. Here the relation is defined by is friend of. A is a friend of B. B is a friend of C. If A is a friend of C, then we can say that relation is transitive. Now, not transitive. Not transitive means we must have A comma B belongs to R, B comma C belongs to R. It means there must exist two ordered pairs like that, and we must have A comma C does not belongs to R. Then the relation is said to be not transitive. Now we come to the example. R6. Let us write 1 1 1 2. You can see here the pair 1 1 1 2. AB BC. 1 1 we can consider it as AB. 1 2 BC. The element 1 1 is common. If we put in the relation of their transitive relation AB BC, so we must have AC. Here it is 1 2. So 1 comma 2. Here the pair is 1 comma 2 belongs to R6. So this relation is transitive relation. Now take another example. 1 1 1 2 2 3. We can see that this relation contains three ordered pairs 1 1 1 2 and 2 3. First two pair forming AB and BC satisfy the condition, but 1 2 2 3, these two ordered pairs AB BC, so we must have 1 comma 3, and in this relation we can see 1 comma 3 does not belongs to R7. So here is a violation of this rule, or we can say following of this. So this relation is not transitive. Just because 1 comma 2 belongs to R, 2 comma 3 belongs to R, but 1 comma 3 does not belongs to R. Here R is actually R7. Okay. Now let us consider another example to clear the concept. R8 equal to, let us write 1 1 1. Now it contains, or more precisely write 1 2. It contains only one ordered pair. So if we come to not transitive, AB BC, here is only AB, there is no BC. So most of the students think it is not transitive, but it is not correct. It is trivially transitive. If we are unable to find the pair B comma C, so we cannot say it is not transitive. We must have AB BC, but AC does not belongs to R to say not transitive. Here you can see here is only one ordered pair. So It is transitive relation trivially. And consider another, that is phi, empty relation. It is also trivially transitive relation. Okay. Now, now one important point is reflexive, symmetric, and transitive. In reflexive relation, we have seen every element has its mirror image. In symmetric, we have seen if AB belongs to R, then BA belongs to R. And in transitive, AB belongs to R, BC belongs to R, implies AC belongs to R. Here the important point is that a relation may be reflexive, may be either reflexive or symmetric or transitive. It is not necessary that a relation is reflexive, then it is symmetric or transitive. All the three types of relation, reflexive, symmetric and transitive, are independent in nature. If a relation is reflexive, then it is not necessary that it may be symmetric or may not be. Now, let us consider example. Let us write a simple example on a set A. 1, 2, 3, R1 equal to 1, 1, 1, 2, 2 and 3, 3 and 1, 2. We have seen this example is reflexive. It is reflexive. Okay. 1, 2 जो है put कर लीजिए. 1, 1, 2, 2, 3, 3. 1, 2, 2, 3. Now we can see that this relation is reflexive. So since all the elements 1, 2, 3 have mirror image, but it is not symmetric since there exist element 1, 2, but 2, 1 does not belongs to R1, so it is not symmetric. Now come to the transitive. Here the pair is 1, 2, 2, 3, but 1, 3 does not belongs to R1, so relation is also not transitive. Now you can see this relation is reflexive only, neither symmetric nor transitive. Also you can consider another relation 1, 2, 2, 1. This relation is obviously symmetric only, 1, 2, 2, 1. Ordered pair in reverse order, 1, 2, 2, 1. It is symmetric only. It is not reflexive since 1, 1, 2, 2, 3, 3 X does not belongs to R2. Not reflexive. Also it is not transitive since here the order we have 1, 2 belongs to R, 2, 1 belongs to R, but 1, 1 does not belongs to R. So it is not transitive. Similarly, we can form the example of that is a relation is transitive but not reflexive and not symmetric. Now we come to an important concept, equivalence relation. Equivalence relation. A relation R on a set A is said to be equivalence if it is reflexive, symmetric, transitive. It means any relation is said to be equivalence if it is reflexive, symmetric and transitive. For example, on a set A, let us consider R equal to 1 1, 2 2, 3 3, 1 2, 2 1. You can see obviously this relation is reflexive as there are 1 1 2 2 3 3 belongs to R. Also it is symmetric. Reverse of 1 1 is 1 1 2 2 2 2 3 3 3 3 1 2 2 1 2 1 1 2. So it is also symmetric. For transitive it has 1 2 2 1 1 1. If you see from here 2 1 1 2 2 2 and all other also satisfy the condition. So this relation is reflexive, symmetric and transitive. It means it is equivalence, relation. Now, identity relation. Or diagonal relation. Identity relation or diagonal relation on a set A. It is defined as R. A comma B such that identity relation or diagonal relation R equal to A comma B such that A equal to B and A comma B belongs to A. So this is called identity relation or diagonal relation. Example, let A equal to 1 2 3, then R equal to 1 1 2 2 3 3 is called identity relation. A comma B such that A equal to B. So it only has mirror image 1 1 2 2 and 3 3. So this is called identity relation or diagonal relation. Important property of this identity or diagonal relation is that this relation is equivalence relation, or more precisely smallest equivalence relation. Smallest equivalence relation. So whenever you are asked smallest equivalence relation on a set A, then it is identity relation, or in other words diagonal relation, defined as R equal to A comma B such that A equal to B for every AB belongs to A. For example, if we consider elements on set A 1 2 3, then R equal to 1 1 2 2 and 3 3. This relation is reflexive, symmetric and transitive. And the proof of this, that it is reflexive, symmetric and transitive, I will give on next lecture.